This is the 30th video in a series that I'm making to support a course in elementary number theory. We just got done talking about the definitions and some basic examples of integer partitions, and then we did a brief stint on generating functions, and now we're going to push these two ideas together. So let's recall some definitions first. So a k-tuple lambda is called a partition of n, and this is the notation, if lambda 1 is bigger than or equal to lambda 2, which is all bigger than or equal to lambda k. So in other words, we have a non-decreasing sequence. And then furthermore, we have n equals lambda 1 plus ... up to lambda k. Also, we say that the function a of q is the generating function for the sequence a sub n as n goes from 0 to infinity. If a sub q is equal to this power series, the sum as n goes from 0 to infinity of a sub n q to the n. So somehow we encode this sequence as coefficients of this power series. And then next we had this little definition here that was really part of our calculations or examples from before. And that is pi sub m of n is equal to the number of partitions of n with parts that are less than or equal to m. And now our first big goal here is to find the generating function for these types of partitions. So I've called that pi mq. I know this is a little bit strange because we're using the same notation for the number of partitions and the generating function, but that's actually pretty common here. Just remember that when we've got a natural number or a non-negative integer in here, we mean the number of partitions, but when we have a formal variable in here, we mean the generating function. So this is going to be the sum as n goes from 0 to infinity, pi mn q to the n. So in order to motivate what we'll eventually come up with, let's do a couple of basic examples. So let's look at m equals 1 first. So notice that's going to be the number of partitions of n using only the part 1. So notice that 1 is equal to 1. That's the only partition of 1 anyway, but it's definitely the only partition of 1 using only 1. And then 2 is equal to 1 plus 1. That's the only partition of 2 using only 1. 3 is equal to 1 plus 1 plus 1, and then so on and so forth. So n is equal to 1 plus all the way up to 1. So there is exactly one partition of n using parts that are less than or equal to 1, and only, in other words, using only 1 as a part. So we can encode that as pi 1 n is equal to 1 for all n bigger than or equal to 0. Recall that when n is equal to 0, we fix the number of partitions to always be just 1. So now let's put this together. That means pi 1 of q is equal to 1 plus 1 times q to the 1 plus 1 times q squared plus 1 times q cubed, and then so on and so forth. So all of these coefficients are 1 because the output of this function is always equal to 1. But by the very important sum of geometric series formula, we have this is equal to 1 over 1 minus q. So that's the generating function for partitions of n using only 1. Okay, so now let's move on to our second example, which you could probably guess is going to be m equals 2. Okay, well, let's do a couple of examples first. So we've got 1 equals 1. That's the only partition of 1 using 1 or 2. In other words, parts less than or equal to 2. We have 2 equals 2 or 1 plus 1. So that's the only partitions of 2 using 2 or 1. And now we can just kind of build from there. So 3 is equal to 2 plus 1, which is equal to 1 plus 1 plus 1. 4 is equal to 2 plus 2, which is equal to 2 plus 1 plus 1, which is equal to 1 plus 1 plus 1 plus 1. So you can see how this might build out. And just as like a little example, this means that pi 2, 1 equals 1, pi 2, 2 equals 2, because we've got 2 partitions. Pi 2, 3 also equals 2, because we've got 2 partitions. Pi 2, 4 equals 3, because we've got 3 partitions. Now, I think it's probably possible to write down a closed formula here, but remember, that's not our goal right now. Our goal is to find a generating function. So let's find that generating function. And we'll do it instead of by putting these numbers as coefficients, we'll write the exponents using each of those partitions. Notice that'll count the same way. So we have pi 2q will be equal to 1 plus q to the 1. So that represents the partition of 1 plus q to the 2 plus q to the 1 plus 1. So that represents the partition of 2. So notice there's 2, there's 1 plus 1. Or q to the 2 plus 1 plus q to the 1 plus 1 plus 1. So those represent the two partitions of 3, and then so on and so forth. So I'll write for 4 as well. So 2 plus 2, q to the 2 plus 1 plus 1, q to the 1 plus 1 plus 1 plus 1, and then so on and so forth. So notice we're counting those partitions by just putting in the exponents. And now we're going to factor this carefully. So let's group all of the terms that do not involve a q squared. So that's going to be all of these that I'm underlining in light blue. Now let's put all of those together. So we'll have 1 plus q to the 1 plus q to the 1 plus 1 plus q to the 1 plus 1 plus 1, and then so on and so forth. Great. And next, let's group all of the terms that have a q squared. So that'll be this one right here. Let's maybe go ahead and underline this in blue so we can see where it came from. So that'll be this right here, that'll be this right here, and that'll be this one right here. But we actually want to skip this one because here we only want to use the exponents of q where we've explicitly written the 2 one time. Here we've explicitly written the 2 two times. So let's see what we get here. So this would be plus q squared times, and now we'll have 1 plus q to the 1 plus q to the 1 plus 1 plus dot, dot, dot. So let's underline that in red. So notice this q squared can be pulled out to give us a 1 from this term, a q to the 1 from this term, and a q to the 1 plus 1 from that term. Okay, but now we can really just keep going. So the next thing that we'll pull out is all of the instances of q to the 2 plus 2. And so we'll have this one, and then we'll have q to the 2 plus 2 plus 1, which is further down the line, q to the 2 plus 2 plus 1 plus 1, and so on and so forth. So that's going to give us plus q to the 2 plus 2, and then 1 plus q to the 1 plus q to the 1 plus 1, and then so on and so forth. And so that goes on forever. And then next up, we can notice that each of these things which are underlined in these different colors can be summed via the geometric series rule. So this guy right here can be summed to 1 over 1 minus q. This guy right here can also be summed to 1 minus 1 over q. This one right here, 1 over 1 minus q, and then so on and so forth. And now look at the coefficients here. We have a coefficient of 1 in front of this 1 over 1 minus q. Coefficient of q squared here, a coefficient of q to the 2 plus 2, which is q to the 4 there. The next one will have a coefficient of q to the 2 plus 2 plus 2, and then so on and so forth. So let's maybe clean up these observations, and then we can write down the generating function in this case. So on the last board, we motivated the ability to write our generating function pi 2q in the following way. So we did some intermediate sums of geometric series, and then we were left with some coefficients, which I've simplified. So this is like our 1 over 1 minus q. So this is only using parts equal to 1. This is q squared over 1 minus q. So this represents partitions using 1 as many times as we want, but 2 only once. This right here represents using 2 exactly 2 times, but 1 as many times as we want, and so on and so forth. But let's notice that this is another geometric series. 1 over 1 minus q is the starting term, and q squared is the common ratio. So we can sum that together to give us 1 over 1 minus q times 1 over 1 minus q squared. So that's what we get in the m equals 2 case. And I think between this n equals 1 and this m equals 2 case, we have a pretty good guess for what it should be in the m equals m case, or the general case. So let's maybe clean up this. We'll state that as a theorem and then move on from there. Motivated by what we saw on the last board, we have the following theorem which explains the generating function for the number of partitions of n whose parts are less than or equal to m. So that's pi m q is 1 over 1 minus q times 1 over 1 minus q squared all the way up to 1 over 1 minus q to the m. We can write that in product notation as follows. So this is the product as j goes from 1 to m of 1 over 1 minus q to the j. Now we're going to prove this by induction, and our base case is actually just done in the examples. Notice we did 2 base cases here, the m equals 1 and 2 base case. So now let's make our induction hypothesis. So that'll be that we suppose for some k bigger than or equal to 1, we have, well, this result holds. So in other words, the number of partitions of n into parts that are less than or equal to k has the following generating function. 1 over 1 minus q times 1 over 1 minus q squared, ending at 1 over 1 minus q to the k. But we could rewrite that with product notation as the product as j goes from 1 to k of 1 over 1 minus q to the j. And now we're going to make the following observation as to how partitions of n might split up. So let's look at partitions of n with parts less than or equal to k plus 1. So that'll be the next case. In other words, the case after the induction hypothesis. And these partitions naturally split up into a bunch of parts. And what are those bunch of parts? Well, we could first look at partitions with all the parts less than or equal to k. So in other words, we're using 0 parts that are equal to k plus 1. And then we could build it up from there. So next, it might be obvious to look at partitions with exactly 1 k plus 1, and then all the rest of them less than or equal to k. So that would be like the next type of partitions of this type. And then maybe just to write one more out, this could split up into partitions with exactly 2 parts that are equal to k plus 1, and the rest are less than or equal to k. Okay, nice. So now let's look at this and notice that these sets over here are disjoint. You cannot simultaneously be a partition using 0 parts that are equal to k plus 1 and be a partition using 1 part equal to k plus 1, and then so on and so forth. And this kind of obviously extends down for all possible values of k plus 1. In other words, using exactly 3 terms that are k plus 1, 4 terms that are k plus 1, and so on and so forth. So that's going to build the following recursion. So how many of these guys are there? Well, there are exactly pi k plus 1 of n of these guys. Then how many are there of this type? Well, there are exactly pi k plus 1 n of that type. Then how many of this type? Well, we've used 1k plus 1, so this is in fact pi k n minus k minus 1. Because after using a single k plus 1, we only need the rest of the terms to add up to n minus k plus 1. And then so on and so forth down here. So this is pi k n minus 2k minus 2. And then so on and so forth. Eventually, you're going to hit 0 because you'll kind of outstrip the size of n. But after that point, you can just set all of these things equal to 0. Okay, so now thinking about this, we can write down the generating function pretty easily. So let's do that on the next board. So after our exploration on the last board, we're ready to write down the generating function for partitions of n into parts that are less than or equal to k plus 1. In other words, the generating function pi k plus 1 q. So let's recall how we built this. So this was built from partitions that are using 0 parts that are equal to k plus 1. So that would be like pi k q. We're using 0 parts that are equal to k plus 1. And then next we would have q to the k plus 1 pi k q. So this would represent using a single part which is equal to k plus 1, and then everything else is less than or equal to k. And then next would be q to the 2k plus 2 pi k q. So this would represent using exactly two parts that are equal to k plus 1 and all of the rest of them less than or equal to k. And then this extends forever. So let's look at what we've got here. We've got another geometric series. Notice our starting term is pi kq, and our common ratio is q to the k plus 1. So that means this sums up to pi kq over 1 minus q to the k plus 1, just by the geometric series summing formula. But now, using our induction hypothesis, we see that this is exactly 1 minus q times 1 minus q squared, all the way up to 1 minus q to the k times 1 minus q to the k plus 1. Which is exactly what we need it to be to finish off this inductive argument. So now that we've got this, let's present a quick corollary of this theorem, which looks at unrestricted partitions. So using the generating function that we developed on the last board, let's prove the following corollary, which is really important. So this is the generating function for unrestricted partitions. So that means we have no restriction on the size of the parts. And also we have no restriction on the number of parts of a certain size, but we didn't talk about that as having to do with this guy up here. So notice this has largest part m. So if we want no largest part like we do here, well, we could just take the limit of this guy as m goes to infinity. So let's do that. So we have p of q is equal to the limit as m goes to infinity of pi m q. But notice that's equal to the limit as m goes to infinity of this product as j goes from 1 to m of 1 over 1 minus q to the j. But that's exactly equal to this product as j goes from 1 to infinity of 1 over 1 minus q to the j, which is the generating function that we're going for. So sometimes when doing calculations, instead of writing it out in this product notation, we'll actually write the terms out because it'll be clearer how we're doing the calculations. So we would write 1 over 1 minus q times 1 over 1 minus q squared, and then so on and so forth, including enough terms so that it's clear how we are manipulating those terms. So now that we've got this nice generating function for unrestricted partitions, let's see the big idea behind this generating function. So on the last board, we determined that the generating function for unrestricted partitions was this infinite product. But I want to recall that each of these rational functions here is really representing this power series like this. So notice this 1 over 1 minus q is 1 plus q squared, which is 1 plus 1, thinking about these as encoding partitions of a certain type. The same thing here. This is encoding the parts of the partition that are equal to 2, and so on and so forth. So let's maybe see what each part of this product corresponds to. So if we were to group all of this together, which is the same thing as looking at this entire rational function up here, these two guys correspond to parts of the partition equal to 2. Okay, so that's what that means. And if we sum it together, that's what this rational function up here means. But what do the individual terms mean? So this individual term right here corresponds to using exactly 2 parts equal to 1, because we've got 1 plus 1. Now that's not really represented up here in the rational function very well. That's represented in this expansion. And then you could see this more generally over here. So this term right here, which is q to the m plus m plus m, that corresponds to using m exactly 3 times in the partition. So if you've got a feel for exactly how these portions of the generating function build up our counting for the number of partitions, you can actually use this to write down generating functions for restricted partitions pretty easily. That's exactly what we'll do on the next board. Now that we hopefully have a good idea for how the parts of our generating function build our counting structure for number of partitions, let's do a couple of examples. So this first example is all partitions using only parts that are 3 mod 4. So let's look at some examples of this real quick. So we've got 3, which is equal to 3. Okay, so that's the only partition of 3 using parts that are congruent to 3 mod 4. Let's see, there are no ways to do 4 or 5 using only parts that are 3 mod 4, but we can do 6. 6 is equal to 3 plus 3. We can also do 7, which is equal to 7. Next, we could do 9 as 3 plus 3 plus 3. So the first several numbers that can be written with parts that are 3 mod 4 only have one partition each. Maybe do a couple of more examples as your warm-up to find which is the first number that exhibits 2 partitions where you're only using parts that are 3 mod 4. Okay, but hopefully by what we saw on the last board, we can just write down the generating function for this. So the first part of that generating function will be 1 over 1 minus q cubed. So that's using parts equal to 3. The next one will be 1 over 1 minus q to the 7. So that'll be using parts equal to 7. The next one will be 1 over 1 minus q to the 11. That'll be parts equal to 11, and so on and so forth. So we can put this all together and have the product as m goes from 0 up to infinity of 1 over 1 minus q to the 4m plus 3. So that's our generating function for partitions who were only using the parts that are congruent to 3 mod 4. Okay, so now let's look at this next example, distinct parts. So that means we're only allowed to use each part one time, or more like generally, or with an eye to more generality, we're allowed to use each part exactly once or 0 times. Okay, so notice 1 plus q is the portion of the generating function which is using 1 0 times, that would be this 1, or 1 1 time, that would be this q. Multiply that by 1 plus q squared. That would represent using 2 1 time or 0 times. 1 plus q cubed, that would represent using 3 0 times or 1 time, and then so on and so forth. So this is going to be an infinite product. So we could write this as the product as m goes from 1 up to infinity of 1 plus q to the m. So that's another important generating function for partitions into distinct parts. So for instance, we're not allowed to use 1 more than once or 2 more than once, so on and so forth. Now let's look at this funny one, which is odd parts used at most twice, but no restriction on even parts. So we'll have to do this a little bit at a time. So that means we can use 1 at most twice. That means we can use it 0 times, 1 time, or 2 times. So 0 times would be a 1, 1 time would be q, 2 times would be q squared, or really q to the 1 plus 1 if you want to think about it like that. So these are our parts equal to 1. No restriction on even parts. That means we can use 2 as many times as we want. So that'll be 1 over 1 minus q squared. Because really we would have the power series 1 plus q squared plus q to the 4th plus q to the 6th forever, but that sums to the following rational function. Okay, so now we're on to parts that are equal to 3, but we're only able to use those 0, 1, or 2 times. So that's going to be 1 plus q cubed plus q to the 6. Then we're on to parts that are equal to 4. We're allowed to use those as many times as we want, so those sum to the geometric series 1 over 1 minus q to the 4th. But now this extends forever. So we're only able to use the odd parts 0, 1, or 2 times, but the even parts are unrestricted. So we can maybe put all of this together into the product as m goes from 1 up to infinity of 1 plus q to the 2m minus 1 plus q to the 4m minus 2 over 1 minus q to the 2m. I think that would maybe be a good description of this generating function. So notice that numerator is talking about how many times we can use the odd parts. This would be using 2m minus 1 0 times, 2m minus 1 1 time, 2m minus 1 2 times. But then down here, we've got no restriction on the number of even parts. Okay, good. So let's maybe get rid of this and we'll do our first theorem using these generating functions. So we're going to finish this video off with a theorem, and this is maybe the simplest theorem that you can prove with generating functions. And that is the number of partitions of n into odd parts, which we will denote by p odd n, is equal to the number of partitions of n into distinct parts, which we'll denote by p distinct n. Then I've written that over here, so p odd n equals p distinct n for all n. Okay, so let's get to it. So let's notice that the sum, as n goes from 0 to infinity, of p distinct n, q to the n, so that's the power series, that is the generating function for partitions of n into distinct parts. We could write that as p distinct q, just using our standard notation from before, but we know what that is from a previous example. So that's equal to 1 plus q times 1 plus q squared times 1 plus q cubed, and then so on and so forth. So I've left a little gap in there because I'm going to multiply each of these by a special version of the number 1. So let's insert a 1 here in the form 1 minus q over 1 minus q. We'll insert a 1 here, 1 minus q squared over 1 minus q squared. We'll insert 1 here, 1 minus q cubed over 1 minus q cubed. And then so on and so forth. That's going to extend forever. So now let's multiply these together. So notice we have a nice product that looks like a difference of squares if we look at each of these pairs like this. And then in the denominator, we've got the product of all of these 1 minus q type terms. So that's going to give us 1 minus q squared from this first blue square, 1 minus q to the 4th from the second blue square, 1 minus q to the 6th from the third, and then so on and so forth. So it looks like the numerator looks like the product of all of these even things. And then, like I said, the denominator will be the product of all of them. So 1 minus q cubed, 1 minus q to the 4th, and then so on and so forth. But now let's notice that a bunch of stuff cancels. So notice this 1 minus q squared cancels with this 1 minus q squared, this 1 minus q to the 4th with this 1 minus q to the 4th, this 1 minus q to the 6th will cancel with a 1 minus q to the 6th down there. And then we're left with 1 minus q cubed, and so on and so forth in the denominator. So let's clean up what we get after all of the cancellation. Okay, so after all the cancellation, we're left with the following rational function. So it's 1 over 1 minus q cubed, 1 minus q to the 5th, and then that extends forever. So let's notice this controls the number of parts equal to 1. There's no restriction on the number of parts equal to 1. These are the number of parts equal to 3. These are the number of parts equal to 5. And then that extends. But there's no restriction on the number of times we can use any of these parts. So it's pretty clear that this is the generating function for the number of partitions of n into odd parts, which we might denote as p odd q. But then that's going to be equal to the sum as n goes from 0 up to infinity of p odd n q to the n. So we have the equality of these two power series, but that means we have the equality of every coefficient of these two power series. But that's exactly what we wanted to show. Okay, so I'll leave you guys with a couple of warm-up exercises. Okay, here are a couple of warm-up problems that are built off of what we just looked at. So let's try to write the generating function for these types of restricted partitions. So the first is partitions of n into parts that are congruent to 1 or 4 mod 5. This is actually interestingly related to the Rogers-Ramanujan identities. So I'll let you guys look those up if you're interested. Next is this kind of kooky one that I came up with, but I think it's maybe a good exercise to get to come to grips with how to write generating functions. So this is partitions of n using even parts an even number of times with no restriction on the odd parts. So that means we're allowed to use 2, 0 times, 2 times, 4 times, 6 times, so on and so forth. We're allowed to use 8 an even number of times as well. So that would be 0 times, 2 times, 4 times, and then so on and so forth. But like I said, we can use the odd numbers as many or as few times as we want. Okay, that's a good place to stop.